What's up, everybody? Today we're here in Chattanooga for the Scenic City Summit, and I've got my awesome room here. We're gonna go ahead and get started, and we will go on. Hello, everybody! Hello. Great. You are here in Chattanooga at Scenic City Summit 2026 for Adaptation of a Self-Taught Developer. Welcome, my brothers and sisters. So glad you're here. Today, we're going to go on a journey that starts with just hacking away at JavaScript and turns into a career, building a community, and learning computer science without even realizing it. Let's go back to 2015, when Left Shark was new and memes were like easy. I was brand new to programming, and in a lot of ways, I was lucky. The cloud was still new, and the internet became commercialized. People were building things online in new and exciting ways. Up until then, I had worked a regular office job. I started a photography business. I had a t-shirt business. I did food trucks and restaurants, and then I did business consulting. And I had no technical background in math or engineering. Then a friend of mine organized a free robotics event for kids at our local makerspace. She put together hardware kits with Arduinos. Make some noise if you know what an Arduino is. All right, great. We had 3D printed parts and laser cut parts, and we built this little two-wheeled robot you see down there in the corner called a NodeBot. And then I showed up and saw 9 and 10-year-olds working on code, making these robots move, and it completely blew my mind. At the time, I had no idea what was actually happening, but now I can explain it. We were using Node.js on the server and sending serial commands directly over USB into a standard Fermata protocol that was flashed onto the Arduino. And that controlled the motors, it allowed it to roll forward and backward. And I just didn't know any of that back then, but I knew if I just copied and pasted enough, it would work. And having the software do something real in the physical world just made my brain tingle in a way, and I was hooked. From there, I spent $300 on an open box Chromebook, figured out how to put Linux on it, and started teaching myself Node.js. I went to my JavaScript meetups that I now run back home, and I used free Code Camp. In a true full circle moment, last year, I spoke at the Commit Your Code conference in Dallas. And Quincy Larson, the person in that picture pointing to the arrow, he was there. He was the guy literally responsible for me being able to become a dev. And I wasn't the only one with that story. Thousands of people have used free Code Camp. So it was just really cool to be able to see him, shake his hand, and thank him for the work that he's done. But do you know what kept me actually motivated during my 2 years of self-study? I was still working a non-tech job, I was raising a newborn daughter, and I was trying to figure out where all of this was even going. I always had that feeling that you might be familiar with after finishing a tutorial. You're like, okay, now what? What is the point of all of this? Then I started realizing that learning this programming thing was opening up new opportunities for me to interact with technology. And this fun picture here is the first time I used an HTC Vive, the virtual reality thing. And my baby daughter, I was walking her around and she fell asleep on my back, but I was like, I can't pass up a chance to use VR for the first time. So she's just totally passed out. Like, I'm just experiencing the future. But what kept me going, my brothers and sisters, was tapping into something unusual. I leaned into a creative force that had been powering the internet quietly for years. Nicolas Cage. Through meme culture, I started to treat Cage as an absurd, inspirational figure. Instead of building quote-unquote serious projects, I applied what I was learning to fun, ridiculous, and strangely meaningful things to me. Learning was really enjoyable before I got weighed down by JIRA tickets and user stories. I started building more and more things, and I took on a persona as someone who has come to earth to preach the power of following Nicolas Cage, using this as a way to push past fear, doubt, and imposter syndrome. I've called it praising Cage, and it became a reminder that you can move forward without having things figured out. You can build first and then understand later, and that your own mind is the thing that's holding you back. So now, even a decade later, join me as we all say praise Cage on 3. Ready? 1, 2, 3. Praise Cage. That's right. We are going to call him down into this room, and the power will come across you, and you will be able to build anything. So how do we get there? I set out to give a talk about learning computer science without formal academic training. And the thing is, I realized that the hardest part is the language that we use to describe it. My experience of comp sci has just been a process of encountering the idea first and later learning the terminology and the definitions. I was told repeatedly that abstractions were a core basis of computer science. Ironically, it was too abstract for me to even understand what that meant. I was already applying the concepts without realizing it. I was using inheritance whenever I wanted to reuse functionality based on relationships. I was asking myself, does this thing I'm building need behavior that already exists somewhere else? Sure, how do I structure that relationship? That's all inheritance was. It didn't really have to be that complicated. I tried reading about object-oriented programming and software design patterns, but I didn't have the experience of building those systems. I learned by changing the color of divs and seeing things go from red to yellow, writing console log, because I could see the result and it was immediate. But when I was reading about how a class flower extends a plant with a method grow, it just didn't connect with me. It just felt too abstract. But as developers, we take deeply human ideas like bank accounts and translate them into logical statements. We write functions that take inputs and produce outputs. But early on, it was hard to map what I was doing to any kind of formal classification. It might as well have been learning about turbo-encabulation and lunar wane shafts. Who in here has seen the retro turbo-encabulator video? Okay, 2 YouTube comedy videos sum up my entire engineering career. One is the turbo-encabulator video. It's from the 60s, and it's just total nonsense science gobbledygook, but it feels so real. The other video is about engineering problems where the title of the video is the expert solution. They call in an expert and they want to make 2 parallel lines intersect. And he's telling them the entire time, you can't do that. And the business people are like, you're just not trying hard enough. Those 2 videos sum up professional engineering for me more than anything else. So it started to feel impossible to learn all of this technical and academic comp sci. I'm just a dude, fueled by intense special interests and YouTube videos. But my brothers and sisters, when I find myself in moments of doubt, when the fear starts to creep in, I turn to Cage. And there is a Cage film that will help me, Adaptation. Has anybody seen this movie before? Yes? Okay, one person. This is great. So, if you haven't seen Adaptation, I'm going to tell you real quick. It was released in 2002, directed by visionary Spike Jonze, and was written by Charlie Kaufman. And it's a really strange meta-narrative about Kaufman struggling to adapt a book into a movie. So what he does is he writes a movie about himself struggling to write the movie. He writes himself into it, played by Nicolas Cage, and he creates his fictional brother Donald, who also is played by Nicolas Cage. So now Nicolas Cage is playing 2 characters, and this movie is all about opposites. Charlie, the writer, is overwhelmed. He's self-conscious and he's paralyzed by the weight of him accepting this adaptation project, while his brother Donald, he's loose, he's confident, he's unbothered while writing his own screenplay. Charlie always criticizes Donald's writing as basic and unoriginal, and Donald is getting things done though. He's going to writing workshops, and then Charlie just spends his time sulking and criticizing others about outside influences being bad on his process. Both are actually trying to be better writers, but they're going about it in completely different ways. I see myself as both Charlie and Donald, much in the same way. Cage plays them both. In my first dev job, I joined a newly formed team at a cloud consultancy, and there was a lot to learn. Not just about cloud, but about everything software development. It was my first technical role. I honestly didn't really understand REST APIs, idempotency, big O notation. I barely understood databases. But what I did know was that I could figure things out and make things work. I could steer the code towards a vision in my head, but it was a very brute force, naive approach, copying and pasting things from Google and Stack Overflow and just forcing them together. That was the Donald in me, getting the results, leaning on whatever patterns were available without questioning them, or never noticing when I was solving the same problem over and over again. But at the same time, the Charlie in me was always present, always an imposter, waiting for a moment when someone would realize I had no idea what I was doing. I didn't know what object-oriented programming was. I didn't know the visitor patterns. And they were going to find out that I didn't understand what everyone else around me grasped so easily. It felt like a personal failure. It felt like I was missing something fundamental, like a dark shadow looming over my gap in my knowledge. But using the knowledge I had learned from NodeBots and building little IoT things, I built an IoT device for my very first conference talk in 2017. At the time, they told me I could use a REST API for the interface to my Arduino hardware, but I couldn't figure it out. But that's when I stumbled into WebSockets and a little JavaScript library called Socket.io. I set up a WebSocket server in Node, created communication channels, and then sent those channels to send commands from a browser to a server. And so what you see here, I took that GIF, I printed it out, I mounted the arm onto a servo, and then there's a Raspberry Pi running Node.js with a web browser. And when you click the buttons on the touch screen, it would make the thing turn. And then I figured out how to send those commands over a remote session. So then I had a proper IoT Nicolas Cage worshiping device that anybody could hit from around the world and make the Lord wave to you, hello and goodbye. It worked. It felt direct and it made sense to me. And once I had that pattern, I used it everywhere. Probably too many places. WebSockets became my default mental model for communication between a user and the computer. The Donald in me was bouncing off the walls, joyous because the system worked. But the Charlie in me was still unsure, still convinced I didn't understand what was going on, and I was resorting to cheap parlor tricks for attention. Looking back, I can see more clearly that WebSockets aren't meant to replace REST APIs or even the other way around. I wasn't making a deliberate architectural decision. I was just adapting to the tools that I could understand and using them to bridge the gap between what I didn't know and what I needed to build. The WebSockets made sense to me because they were a shared state and they were participating in the same ongoing interaction. REST APIs are a different way of thinking entirely. Each request is independent, stateless, and must contain everything needed on its own. I definitely didn't recognize this as system design, and I certainly wasn't thinking of it as computer science. One of the next areas where new learning surfaced was with asynchronous code. I thought code was just something that executed from the top to the bottom in a predictable, linear way. You write one line of code, then it runs, and the next line, and so on. That was the model I had in my head, and it held up well enough for things to get done. Now, who writes JavaScript in here? Okay, one, two, couple people, all right. There is a popular JS comp video that breaks down the event loop within the JavaScript engine. And I watched it so many times and I could not connect the dots. I didn't understand what it was actually trying to tell me. The event loop felt like this invisible thing that I had to know in order to become a programming master. While I was learning Node, I kept hearing about building servers with non-blocking I/O and whatever that meant. But now I know that function calls aren't blocking because it was being scheduled. The event loop is a scheduler. And knowing how things are scheduled reduces the uncertainty of the execution loop, which is actually what the video was teaching. What made this different from earlier learnings was that I just couldn't patch my way through. With harder errors, I could Google for a workaround, but with asynchronous behavior, the system wasn't wrong. My understanding of the loop was. I didn't know how to think in terms of race conditions or eventual consistency. And in this one, I went back to WebSockets. I was an early adopter of serverless WebSockets. And in this project here in the corner where you see all the heads, every head is a current connection. And everyone's phone, I got the accelerometer data through the browser. And as you turn the phone, the heads would turn in real time. And I did this for 2019 serverless conf. And I did another thing with Nicolas Cage where I used machine vision. If it saw a picture of Nicolas Cage, then the app would open up. I used a face of Nicolas Cage as an authentication mechanism. So these are just more of the projects that I've done. But now I can tell you that concurrency isn't just a feature of a language or a single runtime. It's a fundamental property of systems that operate over time periods. Instead of assuming a single flow of execution, I started to expect multiple things to happen at once. I became more cautious about how things are arriving and when and where data is being read. And it's not just a single loop. As I started to get more comfortable working with asynchronous systems, I thought I was beginning to finally understand how things fit together. I had a better sense of timing and how to think about interactions that weren't just sequential. It felt like progress, and I was finally building a model that matched reality a little more closely. And then I came across other kinds of failure. Not one where the code throws in errors and stops, but I was being thrown into enterprise cloud architecture. I saw how hundreds of services were coordinated to record very mundane machine statistics, like calculating the size of email attachments. And this is how our entire modern world runs. I remember working on a system that was just processing incoming events, and in my head, it was straightforward. One request comes in, one record gets created in the database. But then I was noticing duplicate entries. The same event would show up twice, sometimes more, and create another record. I thought the system was broken. What I learned was that I couldn't expect exactly once execution. From the system's perspective, running something twice was safer than not running it at all. That's where I learned about the concept of idempotency. Instead of trying to guarantee that something only happens once, you design the operation so that it produces the same result no matter how many times it runs. Creating a record becomes create this record if it doesn't already exist, and updating a value becomes set this to us, and updating a value becomes set it to this known state and not always overwrite with new data. It's part of how systems remain reliable in the presence of failures and retries and unreliable networks. Now, in a formal curriculum, you'd encounter this in distributed systems and operating systems where you learn about message delivery guarantees. But I wasn't thinking in terms of idempotency and fault tolerance. I was just trying to stop things from breaking when they happened more than once. But what I was actually learning was the correctness in a distributed system isn't about preventing repetition. It's about being safe despite any repetition. That brings us to the states of being. The idea of state is something that I had heard about many, many times, and I really didn't understand it. People talked about managing state machines, front-end state. I had a loose sense that it meant the state of a system, but a definition never just naturally came out to me. It felt circular. I'd ask, what is state? And the answer would just be, it is. It's like, that wasn't what I wanted. But now I see that state is a very concrete thing to the computer. It's not just a general description of a system, it's a particular snapshot of data. It's the value of your variables, the contents of your database, the position of your program during its execution, all held still long enough just for you to inspect it or reason about. That shift was difficult and required letting go of the idea that I could control the exact sequence of events. I had to think about the system in terms of states it moves through and whether those transitions produce a consistent and meaningful result. It's still a concept that's hard to describe cleanly, but once I could see it, I started to recognize it everywhere, not as an abstract concept, but as something tangible, something that happens within a system, and learning to inspect the state of the system gave me debugging superpowers. And then I figured it out, like during the early times of photography, rich dudes were having crazy bets about whether or not all 4 feet of the horse get off the ground when they gallop. So this guy, Edward Muybridge, spends an insane amount of money building several cameras to be able to capture what you see here. And so he built all this technology and spent all this money to win a stupid bet whether or not horses get all 4 feet off the ground. And this is state. This is running state of a horse. You look at each one of these frames and you know what's going on in the horse's system at a particular time. And so this is now how I see states of programs, as a horse sort of running, and we build the machines to capture the state of it as it's galloping along. This must be what it felt like, you know. But not all learnings come from failure, thankfully. I had some good ideas too ahead of time. Some of these learnings come from trying to design things intentionally, from sitting down with a problem and deciding how it should work before anything goes wrong. One example that sticks with me is just a simple system I built around categorizing items. I imagined a robot sorting fruit into 2 bins, a regular bin and a premium bin. Some fruits go in both, while others are only allowed in the premium bin. Each time a robot picks up a fruit, it has to decide where that fruit belongs. Felt like a straightforward problem. You write some conditions and move on. My initial instinct was to define the regular bin by exclusion. If the fruit is not a premium, then it must belong in the regular bin. That worked, and it was flexible in a certain way. As new fruits were introduced, I didn't have to change much as long as they weren't part of the premium category. But it felt indirect. You couldn't look at the code and immediately understand what was allowed, only what was not. So I tried another approach. Instead of defining what didn't belong, I listed explicitly what did. Apples and bananas go in the regular bin, check for membership in the list. That made the system easier to read, but now I had to update a list every time I introduced a new fruit that didn't belong there. I thought I was just choosing between 2 coding styles. It seemed like a matter of preference, like a bike shedding moment. Maybe it was for readability, maybe it was for convenience, but I was actually fighting with how to model a set. I was making decisions about what belongs in a group and how that belonging is defined. That choice turned out to be more fundamental than it first appeared. Defining a set by exclusion or by inclusion doesn't just change the code, it changes how the system behaves and how it evolves. I was starting to get a little mathy, y'all. Like, it was starting to disturb me. Set theory, taxonomy, classification, these are all ways of organizing information into meaningful structures. And in software, it shows up everywhere. It's how we design databases. It's how we structure data and define relationships. The way we define memberships in a set determine how you query it, how you extend it, and how you maintain it. And like so many other moments on this journey, I wasn't consciously applying formal methodologies. I was encountering things in the act of building and only recognizing later that it had a name and it was part of a much larger body of knowledge. And this was different because nothing had broken yet. There was no bug forcing me to reconsider my assumptions. I was just exploring trade-offs. And whether you're designing something from scratch or you're building something on your own, you're always making decisions about structures and representations and trade-offs. Intermission. I gotta take a drink of water. This is the intermission part where I remind myself to get a drink of water. Hydrate if you love yourself. Welcome everybody, my name is Paul Chin Jr. I'm from Virginia Beach, Virginia. Really happy to be here in Chattanooga. This QR code takes you to a page with a bunch of links. One of them is a fun YouTube video where I use the NodeBots and I turn a salad spinner into a DJ controller using nothing but JavaScript. It's pretty cool, check that out. Well, I'm glad we got to take a break because things started to get mathy and I was starting to get scared. And this is where we go completely off the rails and I encounter computational fluid dynamics for the first time. Not as a subject I set out to study, but it appeared when a problem became real enough that my existing models stopped working. Up to this point, everything I've described lives comfortably in software, but in software, things are, even though they're confusing and unpredictable, I could still inspect, log, and reason about them. Bank account numbers, the numbers of paper clips and stuff. But fluid dynamic simulation became vastly more complicated than I ever imagined. It was April 20th, 2025, and I was celebrating 420 when I thought that the bubbling noise coming out of my water pipe was very sublime, and I thought I could build a simulator. The goal was simple: build a physically accurate bong simulator. I called it Hercules. Over 6 months, I went through 9 revisions, and the initial prototypes were sound generators. I generated some tones that sounded pretty good, but it just didn't feel real. I jumped into the project thinking I'd do some geometry and build on top of existing physics game libraries, but I ran into a different class of problem entirely. I quickly learned that modeling air gets really complicated, and there's even more math to learn. As air interacts with water, it forms bubbles, creates turbulence, and none of that fit neatly into the discrete mathematical models I had been using up to this point. And let me see, the sound isn't piped through the room, but I brought V1 of Hercules here. And there's like different sounds we can get. Let's see here. That's the deep chug. And then you got the harsh ripper. It was, yeah, so that was V1. And I was having a lot of fun with it. And then came V9, where I was able to like tune a bunch of stuff. And when you start the hitting, and then you can pull the bowl and then do a release, like it just got more, and I'd still not perfect. I still have a lot of ways to go. But I wanted to show you all those because I found myself just completely lost in some new math. I had been learning to read research papers now, papers on calculating the frequency that a bubble produces as the air envelops around itself. And I learned that they had solved it back in the 70s. It's called the Minart resonance model, and it was from a paper on simulating accurate water sounds. I am now following a path of graphics programming, watching and learning from SIGGRAPH presentations and building like ray tracers and 3D renderers. The cool thing about computer science is that you can go as far down the rabbit hole as you want, and that there's always something above and below the current abstraction that you're in. I'm now far beyond math concepts that I never intended to learn, dealing with discrete systems, individual events, clearly defined states and transitions. That was before. Here, I'm dealing with continuous systems, where change happens over time in a way that isn't easily broken into clean steps. And it's been the most challenging concepts to implement, and I'm having to learn new programming techniques just to deal with the math involved. Turning out, actually simulating reality is really tough. So when people get all like AI psychosed about themselves and like we're living in a simulation, I'm like, bro, it's really hard. It's like all I wanted to do was simulate the bubbling from a bong, and it is so hard. I think if I actually crack it, like that's a real like scientific research prize in there, right? And adapting my thinking now wasn't a side effect of the work any longer. It now is the work. So I didn't learn computer science by stepping away from the work and learning it in isolation. I learned it by adapting my understanding to match what was actually happening, and by gradually building out a set of mental models that became more accurate over time. Along the way, I was constantly searching for explanations. I watched tutorials, sped through YouTube, and read blog posts, and I found people that could explain the thing I was stuck on. You're all here as people devoted to a wide field of knowledge. Getting started is not the goal. Don't worry about being too formal, but the quicker you can name the work, the easier it becomes to find help. I learned that math is not scary because I'm finding real ways to apply it. And YouTube professors do a lot of heavy lifting. I learned from 3 Blue 1 Brown, Veritasium, and Computer File. They beefed up my referential knowledge a ton in the past 5 years. I started to behave like a researcher by accident. I would try something, observe the result, and when it didn't line up with what I expected, that gap became the focus. In Adaptation, the movie, Charlie gets in his own way a lot, but he does have the ability to lay it out and come up with a solution after seeing all the different pieces. I felt the same in looking back at how little concepts build into larger systems of software development that I could become proud of. And when I think back to the beginnings of creating this talk, about the hesitation I have giving it, I think about adaptation. Charlie, he's hired to adapt a book that has no real plot. He becomes fixated on doing it the quote-unquote right way. He refuses to invent drama and impose structure that isn't already there. And he spends most of the film unable to write anything at all. He's stuck, staring at a blank page while the deadline closes in. Eventually, he turns to his brother Donald, the outgoing one, who is writing just another formulaic thriller using conventional writing structures. Against Charlie's instincts, he follows Donald's advice and travels to meet the author he's trying to adapt, inserting himself into a story he couldn't figure out how to tell. From there, the film shifts completely. It becomes the kind of film that Charlie was trying to avoid. It had action sequences, confrontation, violence. It was not the pure adaptation he set out to write, but it became a finished story, one that only exists because he allowed the process and himself to change. The movie is about exploring passion. It's about overcoming the need to become perfect, and it's about creating connections in the world, because life is better when you live outside your own ruminations. It's about recognizing the scared parts of ourselves, creating a version of ourselves that is more confident, and trusting that growth will happen when we put in the work. I wanted to talk about computer science without using the language of computer science. I wanted to avoid familiar structure with slides that said data structures and algorithms, compilers. and I instead wanted to show something more honest and grounded in experience. But at a certain point, I have to accept that those structures exist for a reason. The concepts are very real. Terminology matters, and trying to avoid them completely was just another way of me getting stuck. The tension between wanting to do it the right way and actually doing it at all never fully goes away. The part of me that wants to understand everything and the part of me that just wants to build will always be there. And in the same way that Charlie ultimately has to let go of the version of the story that he thought he was supposed to write, I had to let go of the version of learning that I thought I was supposed to follow. Not abandon it, but to allow it to change into something that could actually exist. We have to learn to adapt. Praise Cage!
Praise Cage!
Thank you! Yeah, let's go.